Video, I'm going to talk about penalty methods that are used in the optimization problems. First, I want to explain why do we need penalty methods in the first place. As you know, in optimization, and we're interested in nonlinear optimization at the moment, in nonlinear optimization, there are two types of optimization problems. The first is constrained, and the second is unconstrained. And the question is there a way that we can turn a constrained optimization problem into unconstrained optimization problem? And the answer is yes. And we're going to use penalty methods to achieve that thing that we are talking about here. And of course, the best way to explain is to give an example. And I am going to give you an example of constrained optimization problem. Then we're going to use penalty methods to turn it into an unconstrained optimization problem. We have an objective function fx ten. And we have one constraint that says x should be bigger or equal than 3. And we're going to use a penalty method to incorporate this constraint into our objective function, and then only work on that objective function. Without any further explanation, I will write something, then after finishing writing it, I will explain what we are doing here exactly. Okay, now we have a new function, and this function has actually two variables, x and r. And we introduced a new variable r, and it's called a penalty weight. And if we observe this function closely, uh, what we see that if we if we satisfy the constraint, which is x is equal or bigger than 3, then what happens here? Let's see. So this minimum function here returns the minimum of between x minus 3 and 0. And if x is 3, then it will just return 0. The constraint is satisfied, and there what we are going to left with is just fx, and we're going to minimize fx. It works. But if the x is smaller than 3, what's going to happen is that it will be something like 2. Let's say it's x is 2, it's less than 3, the constraint is not satisfied. It will be minus 1. And of course, minus 1 is bigger than 0, and we're going to have fx plus 1, because minus 1 square of minus 1 is 1. For some r, we chose r. We are going to give different weights. And as you can see, what's happening here is that as we move from the constraint, we created a function that is increasing proportional to how much we violated the constraint. If we violated the constraint, let's say 5 units, then we will it will add to the original function of fx more. And if we violated the constraint like let's say 10 units, then it will add even more to the original function here. And geometrically speaking, what we see here, we're going to draw the graph of fx first. And let's say this is a constraint. For the purpose of having a clearer graph, I'm going to draw this more like this. Actually, it doesn't matter. It will be the same for other graphs as well. So let's say this is our fx, the blue graph here, and this is x equal 3. And as you can see, what we're interested in is this area, right? This is the feasible region that we're interested, and this is the region that we're going to find the minimum x. And what we can see here is that if we try to plot the function of x and r, what we see here that if the constraint is satisfied, then it's going to return 0, right? Then it means that this function will be the same as our original function if the constraint is satisfied. So, if it's the case, then x bigger than 3 part of the function, it will follow the same path. It will be exactly the same graph because x is bigger than 3, and that's why this function is going to return 0. And it doesn't matter what is the value of r, because if it's 0, then the whole expression here will be 0, and we're going to left with fx. But what if the constraint is not satisfied? If the constraint is not satisfied, starting from this point, based on the value of r, it will diverge from the original function. If the r is big, it will diverge faster. If the r is small, it will diverge a little slower. And let's say r is we gave r 0.5. Then it'll be something like this, right? Let's say 0.5. I'm going to draw the diverged part of fxr with the green. R is 0.5. Let's say now r is 1. Let's say 0.8. Now it will diverge a bit faster. Oh, here. Let's say r is 1. And let's say this is going to happen. And as you can see, what's happening here is that as we increase the variable r, the minimum point of xr is actually our solution. Because let's say before in the original graph without constraint, this was the minimum point, right? This was the minimum point. But after some steps, after we increased our several times and we ended up with this, for example, with r is 1 and this is our function, we ended up with this function, with this one, right? With this one. And as you can see, the minimum of this is here, which is the solution of our objective function subjected to this constraint. Okay, this is the basic idea behind incorporating the constraint into the objective function to get rid of the constraint and turn it into a constraint optimization problem. And I will write a couple of more things like how we do it to explain. So what is our goal is that we are going to maximize R, and we're going to minimize x of fx r. What does it mean here? It means, let's say fx, this is our function. We start to solve this problem by giving R a value. Let's say we started with 0.5. We started with 0.5, then after giving a value to R, let's say 0.5, it was this function right here. Here, this one. And then we calculate the minimum of this function. So after giving, in the first iteration, we gave R 0.5, then we minimize that function. We find the x that minimizes that function. Then what we do next, for example, let's say in the first step we calculated the minimum of this function, right? This one here. Then let's say the minimum is, we found that minimum x is here, something like that. X is 4. Let's say x is 4. So then what we do, again, we increase the number of r, the value of r. We increase the value of r. Then we again minimize this whole function. Then let's say in the next iteration we got x point x equal to let's say 3.5, and we do it iteratively. We iteratively increase the value of r, and then in each step we calculate the minimum of the objective function. And when we stop, as you can see that after some point here, it doesn't matter how much we increase the value of r, the minimum of this function will stay the same, right? We got this, it was in the first value of r when it was 0.5, then the minimum was here, then it's here, then it's here. And after some time, it doesn't matter how many times we increase the r, how much we increase the r, the minima will stay the same. And when we see that the values of the minima are the same in the next iterations, then we stop. And that x will be the minimum of our function, objective function, but at the same time, it will satisfy the constraint here. That is simply the penalty method when in optimization problems.